The following content is provided by MIT OpenCourseware under a Creative Commons license. Additional information about our license and MIT OpenCourseware in general is available at ocw.mit.edu.
Yeah, I'm Tony Diaz. I have 25 years or so experience in boat building and boat design. And that stretches from hand-carved models and hand-drawn lines to CAD work. And my main interest really is not just restricted to designing boats, but what designing boats can teach you about designing anything, or figuring out a very, very complex set of parameters and coming through to useful decisions. So I don't know if we start with
Sure.
you.
I'm Chris Chen. I'm a first-year student in the master's program in architecture, and the interest is pretty general. It's a very interesting form, and just checking it out,
Great.
See how it is. Yeah. Great.
Do you have any experience with boats at all? No? Okay.
Not in terms of construction
Or use, or have you ever sailed?
Pretty
or?
limited. No. Yeah.
Okay. All right. So we'll just go around up and down.
I'm aware. I'm planning on being a course 2. I'm a freshman. I was going to learn a little bit about boat design. No experience with boats.
I'm Sebastian Severo. 2OE.
Say that again?
Sebastian Severo.
Okay, thank you.
2OE, mechanics and ocean engineering. I've taken Introductory Lecture.
Great.
My name is Dwight Chambers. I'm a senior in nuclear engineering, and I rode for several years, so I wanted to know how they work.
I'm Prof. I'm in the architecture program, master's program, and I'm just taking this class, like you said, to explore more parameters.
My name is Marcus. I'm a 4th year in course 2. I know nothing about boats, but this is the first IAP I've had free to do whatever I want, so it sees me opportunity.
Okay.
I'm Allison Brown. I'm a 3rd-year geology student, but I joined the sailing team for the first time this year, and I really loved it. And I kind of played around with model boat building-ish a little bit, and not anything serious, but so.
I'm Reuben. I am course 6 with electrical engineering and computer science. I have some experience sailing, and I'm currently on the crew team. So.
All right.
I'm Justine. I'm a freshman, and I'm planning to declare 16. And I don't know. I just started.
What is the course 2 is OE? Is that right?
Course 2 is mechanical.
Is mechanical. I'm sorry.
Course 16 is aero-astro.
Oh, yeah. Okay.
Okay.
All right.
Yeah.
Cool. Yeah. I'm very much interested in aero too, so we'll have plenty to talk about there.
That has a small role in both.
Yeah.
It also, just so you know, I work almost entirely alone all the time in a shop, in my little cloistered environment. So if I'm hard to understand, let me know. I'm not fragile about that at all. So let me know if what I say isn't clear. I've done a lot of boat building workshops, as has Tony, so I'm not unfamiliar with the world, but please just stop me if something makes no sense or if I'm uninterpretable. Okay. One of the things that we want to talk about, with us, we're talking about a fairly antiquated method of boat design. We've picked this method of half model carving and developing lines. It's very dated. But what we really want to have you do is experience the method, because it has certain strengths relative to contemporary design methods. And the goal of the class, what we really want from you is just to be involved in the thought process. We don't want you to get hung up on how to carve and how to use the tools and how to draw the lines plans, which experienced people maybe never use again. We wanted you to think about this as a tool to understand a design. That's the main goal.
The material that we're going to be skipping over could easily be a 2-year, 4-year course. So yeah, no. The idea is to to become acquainted with or to bounce off of concepts as they come up and as they somehow attach to you somehow. But not, in the end, this isn't a course about making a pretty half model or about designing a boat. You're not going to design a boat in a week, okay? So, so go ahead.
Yeah. On that note, one of the things about this method is that, you know, one of the limitations of it is that it really relies on your own understanding of design. You know, the old builders, when they were carving a half model, they're really working largely by eye to determine a shape. And so they were limited in their thinking by their own experience. They got to be pretty good, but there are real limitations in that way. It's hard to really step out and make something really new. And also the process of designing in this way, if you're, you know, especially in the era that this method was in its heyday, from roughly 1810 to, you know, 1950 or so, probably, designers would, well, actually, people went to drawing just by lines, much earlier than that, but you know, the builders would carve their model by eye, and then they would do some kind of trick to pick up the shape of the model, draw it on paper sometimes, or draw the model, draw the line span, which you'll see full scale. So if you have a 50-foot boat, you make a 50-foot drawing. And that drawing is what you pattern from. But the point of that exercise, we'll go through that in big detail, but the point of that exercise is that every step of it is an opportunity to think about iterations of the design. So, you know, one of the things that we ask of you is not to marry yourself to your model, not to make it smooth and shiny, but to think of it critically at every step. And so when you carve your model, which we're going to do pretty quickly, you're going to be done in 2 days, basically, and then go into drawing the lines plan, that's another opportunity to redevelop the form. And if you're building it, you would have another opportunity when you lofted it, and then you have another opportunity when you built it, you know, to change it at every step. So you never get a chance to sort of stop thinking, you never get a chance to stop being critical. And then later on, if you're the builder and the sailor, when you're sanding the bottom, you know, one year, you're looking at it and think, boy, the next boat, you know, I'm going to do this differently. So that's how this process works. It's visualization, but it's also understanding this as a dynamic object. It's not a shape. This is an abstract representation of the boat, of the performance of the boat. You know, how it's seakeeping, how it would act, how it looks heeled over. You're visualizing the sail rig, obviously, in this case, but think of it as a dynamic object, not as just some sculpture.
I think it'd be a good time to kind of recapitulate the evolution of how boats were designed, because in European history, European and North American culture, back in the Middle Ages and probably even going back into ancient times, boats were designed basically on a method that had to do with taking an arc of a circle and then somehow doing tangents off of that circle. And if you can imagine back well, we'll see models this afternoon, but of 16th century sailing ship, you know, basically it's a big round middle with ends that more or less you know, fade in and out of that hemisphere that's in the middle. It was called a hole molding, basically the technique that was used. And basically you made one shape for the middle, and that's all that a master builder needed. Kind of like a cathedral builder might, you know, have a triangle and a plumb bob and would design a cathedral, but basically, as he built it, these builders using this one master mold could then build a ship, or if they wanted a bigger ship, they'd just make it longer, or make a slightly larger mold that was exactly the same shape, the same type of shape. So then from that,
could I just vamp on that? One of the ways that, you know, those rules of form, like that curve might apply to the deck line in this view. It might apply to the curve of the hull, you know, sectionally here. In a boat with recurve, you know, it might apply down here, you know, this curve. So all of these are these arcs, and so the builder might have one or two of these battens, and that's all he has. There's no drawing. Right? There's an idea of overall length, and they would lay that on, and they would actually saw out the timbers. The frames are all sawn. And so you just saw those things out. Then it relied on the builder to look at that shape and connect the dots, right? You know, by making it fair, which we'll be talking a lot about, fairness of lines. So they'll be running big battens over these frames, and then with the little adze, just dubbing down the frames, just taking off some wood to bevel them and make it all blend.
Yeah.
So that, I mean, that's an example of the builder really is designing the boat. The designer is saying, okay, I want this, and this, 50 cubits by 300 cubits or whatever, and the builder does the rest.
Yeah, and that kind of relates to architecture, I would think, in the sense that you're taking a basic geometric shape, in this case a hemisphere as opposed to a right angle, and you're saying, well, whatever I make is going to be harmonious and come out to a whole because I'm limiting myself to articulating one form.
Right.
Then the Enlightenment happened, I guess, and people started going wild and thought that perhaps they could have a more complex way of dealing with the problem, and started to get a sense that well, the front of the boat had a different function than the back of the boat, and that there was a little bit more to it than could be handled by just using one shape and just adjusting it everywhere. And so the empirical process of carving a scale version of something to kind of be able to take these more complex ideas and put them into a manageable form to then bounce off of and further articulate and to hopefully do some sort of analysis of that form, and then have a record of what you've done, so that then someone then could, yourself or someone else, could then build from it. And then that progressed for a number of years until then gentlemen decided that they wanted to get in on this, but they didn't want to get their hands dirty. So they brought in drafting. And some of the earliest really great examples of marine drafting are the British Admiralty drawings from the 17th, 18th century.
Which really were just records of ships that worked, rather
that
than
were
designs to
right.
build to.
Right,
Yeah.
right. But once that technique had evolved, then when you get into the 19th century, certain amount of basically yacht design at that point started to be done more and more just on paper. There was a kind of a way to take it out of the workroom and bring it into the office. And the advantages there, of course, is that once you've abstracted one step further from a physical reality, which means that you can experiment a little bit more freely, and it's also using measurement techniques and mathematics. You can then start to imagine that you're actually analyzing what you've got in a more intellectual manner, and then that sort of peaked in the middle of the 20th century, and then once first the use of computers started, of course, came in more inexpensive, kind of military naval kind of way, when computers were still very big and bulky. But then, as soon as personal computers came on, people started to figure out ways to kind of, in a way, return to a 3D world, but do it in a virtual 3D world, and can marry the two advantages of the physical model with the abstract drawing version, because with a CAD system, basically you're virtually creating a model that you can look at and almost touch as well. Once you put it out, you can put it out in a 3D printer or something, so you actually can touch it. But you're getting a lot of the advantages that you had in this style of design and analysis, but at the same time, you're taking all of the mathematical analysis that became available with the hand drawing, and you're automating a lot of that and speeding up the labor involved in that, and you're able to become more and more fine-tuned in how you're able to analyze. So I guess for now that pretty much covers, I think, the arc of the way in which boats have been designed, and the way in which this particular project that we're using as a framework this week is going to fits into that overall view.
Yeah, I think one of the things about that story that's interesting too is that the whole process is one of which designers exerting greater authority over the finished product. It was really loosey-goosey with a hole molding system, and then a half model system. It relies on the builder to loft the boat, to draw that full-size drawing of the line plan, which is correcting the plan that's drawn at too small a scale. But it's also interpretive. Every step you're interpreting it, and if Tony lofted the boat and I lofted the boat, there would be differences. Mine would be right, of course, but never mind that. But there always are these. But now, of course, if you have a computer design and you have the molds made by a CNC milling machine, then that interpretive process has been taken out. The designer gets full authority in the finished product, much more than before. And it's just differences of the method.
Yeah, and then just also, Reuben touched on this before. The kind of the New England builder designer of the 19th and even through the 20th century, who built either small sailing yachts or lobster boats or something like that, would have grown up in his father's shop, sweeping the floor and just sort of absorbing that whole environment. Would start building, carving models as toys when he was little, and of course these were all, pretty much all men and boys at the time, and then sort of absorb the whole environment and the whole set of limited but precise experience that was in that lineage that he grew up in, and at that point would know through the stories told by grandfather and his father and all the boat users, fishermen or whoever who hung out in the shop, would have a broad kind of imaginative sense of what the implications were of the particular kind of boat that they built. But they would never dream of saying, okay, well, I built a 30-foot lobster boat, and we have been evolving this for 3 generations. That, all right, well, now next week I'm going to build a catamaran sailboat. I mean, there's just absolutely no way that someone from that tradition would jump like that. For them, a big deal would be to go to making it a 10% bigger or somehow change the tiniest thing, and people would really have very strong opinions about how all those little particular things mattered. Some of it was caution because there were no more empirical way, more analytical ways of making judgments, but a lot of it was grounded in just really strong empirical understanding. Whereas now, someone designing boats at least has imagines that they can jump between all sorts of styles of boat types or whatever, and because of the power of the tools they have available and the information that they have available, that they can pretty much grasp enough of whatever it is and jump in. So that's a real significant difference.
Yeah, absolutely. And it's also limited to symmetrical boats. They have to be, you're only carving half for obvious reasons, saves a lot of time, and it's really hard to make 2 identical halves. So there are limitations like that, along with that iterative process. And also, here's this thing that, like Tony was saying, a lot of these boats would have the same sail plan, or would be powered in the same way, they'd be rowed or sailed by familiar rigs that they understood very well. But you walking in here, unless you're a sailor, how do you picture the rig on this boat? It does rely on that experience to know it. And so I think that's one of the big limitations of the method. Yeah. But it did free up people to rethink that those hole molded methods that allowed for constantly changing radius curves, etc. But there, as you'll experience when you're making your models, there are real similarities with the hole molding, because you're going to work out basic sort of perimeter lines. This deck line, the profile of the boat, and they're going to work out maybe a transom shape, maybe a midship shape, and then you're going to blend all that in, right? Like that old hole molding boat builder, right? Who has just a couple of lines to go by, then make it all work. and that's your design process, right? So I think a lot of times those old New England boat builders, they carve a model sitting by the fire in the winter, and they throw that one in the fire and just carve another one. If they blew it, they would just keep trying it in that way. And their models were really crude. They didn't look like this at all. We'll see a bunch of the building models.
Another thing you're bringing up too is that there's a certain similarity between a half model and a towing tank model. I mean, you may have either seen or heard about, and the museum here has quite a few. There's full models of some fairly good size scale that were actually towed in a tank, or even some smaller models that certain designers have used that they tow behind a boat. But those are all full models, and those were intended. Those were analytical tools, used to try to compare. Once you're trying to fine tune a boat to compare performance one versus another, or to create parameters that then you could try to theorize how those parameters might apply across a broader range. But that similarity, I mean, these models are just meant to capture a shape that you arrive at out of whatever understanding you bring to it. But they're not going to then give you any information back out about how they're going to perform, unless from one of these models you actually went to the trouble of making one of these towing models.
So everything that we've said, we're going to say again and again. Yeah. So I mean, we've given you, that's the whole cell pretty much right there. But we'll extemporize a lot on that. But in the context of you doing the work, so we'll keep the talk as limited as possible for now. But just so you know what we're expecting in the class, we brought in those pine blanks, those little rectangular forms. Those are your blanks, and basically what we're going to do today is we'll begin the process of thinking about, this morning we'll begin the process of thinking about what you want to design. And then we're going to go to the half model collection at the MIT Museum. It's wonderful. This is like, going to Mecca for me, looking at these old models. So we'll go to the half model room and you'll get a whole range of ideas. I brought a few of my models for you to look at for different ideas about what different hull forms are. And then this afternoon we'll begin drawing on those blocks. Some of these, what we're calling the master lines, a deck line and a profile. And then probably tomorrow morning you'll begin carving. So
I don't know how obvious it had been up to now that everyone had to kind of come up with some sort of boat that they wanted to carve. But let's be clear about what that really means right now. Some of you row, and some of you have done some sailing. Others have kind of a broader interest. Now, you can bring whatever specific interest you have into it, or you can kind of be, if you don't have a specific interest, you can be a little bit more whimsical about what the start of the idea is. You can just pick up on something that comes up during this preliminary part of the session and jump on that and say, okay, that's where I want to go. But no matter which one of these starting points that you decide on, I think it's really important that that you keep yourself open to the way in which even an experienced person can't bring too many preconceptions into this, and that is how deadly it would be for a beginner to say, okay, well, I already know exactly what I want to do, and now just get out of my way and let me do it. That would be fine if we had another couple of years for you to kind of trial and error your way through this, but in the end, that might or might not actually make you understand, get you to understand these things any better. I think that the real goals that we're aiming for here, and the greater satisfaction from the course is going to come from being able to, have some sort of a fairly solid starting point and say, okay, not every, between now and tomorrow morning, keep switching between an oil tanker and a catamaran, but pick a type. but then remain open as to how that's going to flesh out until we actually do it. You know, this is empirical work. This is something that where, you know, every step adds on, you know, builds on what came before, and none of us should really know where we're going to end up before we've begun. Just have a kind of a general direction.
Yeah, and you know, that's what's that right there might be what's unique about this method, because that attitude is really logical with it. And so, you know, to that end, you know, no one's going to be graded on the quality of their design at all. You know, the biggest thing that we want to see is, you know, go around the room, be aware of what everyone else's model's looking like. You know, take the whole, you know, get the whole picture, and just, you know, just stay heavily involved with that way. So just continuing with how the week will go. Tomorrow and Wednesday, we're going to try to get all our models more or less, you know, that idea basically fleshed out and done. So the models will be almost completely shaped as of Thursday morning. Everything's going to be fine. And then on Thursday, Tony's going to be gone Tuesday and Wednesday. And Tony's expertise obviously is far better than mine for critiquing the model from a design perspective, because I'm not a boat designer, I'm just a builder. I've got experience with the method, but I can show you a lot how to use the tools. I can show you a lot about how to understand the system. And then Tony will come back on Thursday, and we'll begin lifting shapes. You know, taking offsets off your models and beginning to draw them. We probably won't do everybody's model, simply because I don't think it'll maximize the class to do it. We'll probably do a few though. We'll try to get some shapes picked up on Wednesday evening or Wednesday afternoon. And so then Thursday is beginning drafting and understanding how that's interpreted as well to the process. And then Friday, we're going to try to wrap this whole thing up, which it ends up being a lot of fun. But we'll talk about some of the old analog systems for analyzing the drawings. And we may go back to the model room for another vision of that. We'll go to Kurt's plans collection, which is, you know, a fabulous resource for you guys at MIT. The plans collection here is unreal. So that's basically the deal with the class. You know, the schedule is 9:30 to 3:30. It's really brief, you know, to do everything that we want to do. If you can bring your lunches, that'd be great, so that lunch can be like a half hour, not 45 minutes. And I really do want everyone to be here at 9:30. But I hate to say this, inevitably there'll be stragglers, but we want to introduce every day with a pretty brief morning lecture. Like tomorrow morning, I'm going to start demonstrating how to carve the models, you know, how to use the various tools. Another thing on the tools that, you know, they're the shop tools, but also Tony and I have another organization called Mass Bay Maritime Artisans. This is a nonprofit that does boat building workshops based out of Kingston, Mass. And I brought all the tools. So we have, I think we have like 9 block planes. You know, we have a lot of chisels, we have a lot of spoke shapes, we have a lot of the tools that we need, and they're all tuned up and ready to go. So we have all those tools as well to use. But that's basically basically how the class will.
But you know, this isn't a craft class. You're not going to learn how to do any kind of woodworking technique. We didn't really talk about anyone who has had previous woodworking experience or not.
Yeah, we want
you guys might, you might have none right now. You might actually be very experienced woodworkers, but these process, this is more of an experimental class. Think of these as being, the beakers or the computer algorithms or whatever it is, or the circuits that you would use in any of your other classes, and they're means to get to an understanding. They're not an end in themselves. And the fact that someone has limited experience with tools, Reuben's very good at helping people out with those things. And the thing is that it isn't a race to see who has the shiniest model at the end of the week. If someone is just totally incapable of the physical work, which I probably would have been, the first time I'd been exposed to this, that's still not a barrier to the class because you know, having some attempt at doing the physical work and watching and talking and listening will fill out all of the gaps. As long as at least a couple of you can actually make a workmanlike attempt at you know, at something with some level of accuracy to it, but that's not really a big expectation, and that shouldn't be a big hurdle for anyone.
Yeah, and it's really on us to keep you from getting caught up in how the tools work and make it, you know, just try to think about what your idea is, what the form is, and like Tony said, I'll be hovering a lot and trying to show you how to execute that idea. So I was going to talk about that jig, but I don't think it's not in the room. So let's do that later. What time is it, Tony?
If this is still working, it's only 10 or 11.
Oh, good.
Is that right?
Good. So let's well, any questions? Yeah, right. Anybody falling asleep yet? You look pretty lively. Let's begin thinking about then. We want you to go to the model room with some idea of what to look for. You know, some idea of what the shape you want to think about is. I mean, the model room is, you know, it's just what's in there. It's a lot of variety, but it's just what's there. There may not be the design that you're really thinking about, and that's fine. But let's begin in a kind of in a group way to begin thinking about your models. What are you thinking?
Well, I'm just thinking we've got at least 10 minutes before we need to do something else, right?
Yeah.
Would anyone want to volunteer to start either asking a question or making a statement about what they think, how they think they want to begin, or what kernel of a germinating idea they have about where they would like to come, you know, to start focusing your particular boat project. Because if someone's willing to volunteer just a little kernel of that, we can kind of bounce that around, and perhaps this can start getting concrete for you. Yeah.
Before you do that, is it possible to speak broadly about sort of, I mean, you mentioned sort of like classes of boats or kinds of boats.
Right.
Can you describe briefly, like sort of underlying categories?
Well, that's going to be really very, very easy to do in the model room, and but if you know that would come up during this little bit, this exercise that I'd like to do right now.
Yeah. And
well, I think you could get into that a little bit. I mean, there's a whole class of shapes that you're not going to see in that model room. I mean, for example, some of the most high-tech hull forms on the planet today is swath ships. Has anybody ever heard of the term swath? You know, this is a sort of a hybrid between a submarine and a catamaran. And the blocks that Reuben has brought are, unless you're doing extremely small scale, are wholly inadequate to be able to do that. So, you know, there are a lot of, we are seeing today some change in this long evolution of hull forms that you won't be able to represent. And I could say, you know, I've seen some presentations on these hull forms, and they're wild hull forms, and that would be extremely cool thing to try to model. So that's there are real limitations on. And, so, I think that's another thing to think about too. One of the great things about MIT is that there's great ethnic mix here, and so anything, whatever's familiar to you, whatever you think, whatever, you know, it really could be. I think because this method is relying on your own assumptions to begin with, and then critiquing your own assumptions. You know, whatever your assumptions are, then it just doesn't matter at all. And you know, the method is very traditional. You know, it's suitable, like Kirk's pointing out, it's suitable for traditional boats. It's suited very well for round bottom boats. You know, boats that are curved constantly in this plane. If you cut it right here, you have a nice curve here, as opposed to a series of chines or one chine. The method is much better for round bottom than for boats with.
Well, I guess until someone jumps up to testify to what they want to do, just broadly speaking, I mean, we are making a few very broad assumptions. Let me just sort of clarify what those are. We're basically coming from a pleasure boat world or pleasure boat mentality. We're basically thinking about boats that that any of us might actually dream about either owning or operating at some point without having to pledge an oath to a military. But within those that we could say that that's an arbitrary limitation, but we'll just take that as a given to start with. And if anyone wants to argue a point to broaden that in some particular way, we can certainly listen to that. But if we take that as a basic assumption, then there are human-powered craft, like the different rowing boats, and there are sail-powered craft, and there are engine-powered craft of some sort or other. Reuben's experience is mostly in the human and sail-powered, as is mine. Although we both have some experience with motor-powered, powered craft. Then there, within those three types and across those three types, there are boats that are created from a set of simple surfaces that are flat in one plane or another, and create different curved plates to create the shape of the boat. We've kind of basically made this assumption that we're most interested in boats that are made out of compound curves. They're a lot more interesting, and if you take out, since we're not necessarily creating, they're also the most ambitious shapes to deal with. So there's a lot more to kind of sink in our teeth into there. The boats made from flat planes they were mostly, for the most part, or almost always, there were compromises to do with technical limitations of the builders or economic limitations of the owners to try to kind of make something really simple that would still work. For the most part, you never end up with an optimized shape by starting from just a series of flat planes. So within each of those categories, there are round shaped, complex shaped boats. The other two basic categories are boats that displace water as they move totally, which means that whatever they weigh is what keeps, they have an amount of buoyancy to that water line, which, like on this model, the water line is this one right here. The volume of this part of the boat here displaces enough water to support the weight of the whole structure plus the whatever cargo or crew or capacity the boat's supposed to carry. And the boat is always working in a fully displacement mode, which means that the weight is always being supported just by buoyancy. And then there are planing boats or semi-planing boats that actually, through use of more power, whether it be sail power or engine power, and a certain kind of a shape, actually start to take advantage of the hardness of water at speed to actually start to plane on top of the water, and at that point they're no longer having to push that water aside and then let the water come back behind them, but they're actually skipping like a stone skipping across the surface of the water. And those basic two types vary because on the one hand, a displacement boat is you couldn't dream of getting into a planing hull without enough suitable power, which means either a very light construction and a very big sail rig, or a motor of some sort. So without a lot of power, you can't get involved in planing. But vice versa, with a planing boat, you have different challenges with making the thing seaworthy enough to be able to survive certain conditions or whatever, or to have enough capacity to you don't have planing oil tankers because they're all about maximizing capacity, and of course if you were trying to make this thing fly over the top of the water, you couldn't do that. So we're going to get more and more into the there's always a set of trade-offs. There is going to be a primary reason for trying to follow a certain tack, but then there'll be secondary reasons that if too many of those pile up will mean that we'll want to shift direction and head a slightly different way. But at this point, we could just go on and on with endless abstract discussion, which would certainly fill a year. But it'd be much better to start to just be very specific about what your projects are going to be.
I have a quick question, actually.
Sure.
I know a lot of boats are, I guess they use more of a convex shape, sort of. Is it possible to use sort of like a concave thing, especially towards the front or the back? Just like
sure.
kind of like a combination of concave and convex?
You're always, you see, one of of course, the most fascinating thing about boat design, part of boat design is actually how a boat goes through the water. It's not all of it, but it's a big part of it. But one of the really fascinating things about boat design or aeronautics is that you're dealing with pushing a shape through a fluid, or in the case of a boat, actually through two fluids, water and air, and a boundary layer. So a lot of what we're going to be dealing with is thinking about fluid dynamics in a kind of an intuitive way for the most part. But when you think about curves, and also you see, we're basically talking about curves, curves in 3 dimensions, and the implications. I mean, basically the reason why there are curves in the boat are that on the one hand you want to have a certain capacity to carry whatever it is the payload of this thing is. And on the other hand, you have to try to force this through this fairly unyielding medium. And depending on how much power is available, this is either going to go slowly or it's going to go quickly, or how important load capacity is versus speed. The thing's going to be either bigger or narrower. But basically, if things are very round, they're probably going to be very slow. And we can talk about why that is, but basically that's fairly obvious that you're taking all these molecules that have a lot of density to them and you're pushing them out of the way abruptly, and then you're asking them to bounce back together abruptly. If you try to do that beyond a certain speed, you're just going to create a tremendous amount of turbulence. And anytime you set water molecules moving other than where they're going in the first place, you're adding energy to that water, and you're doing that by whether it be your oars or the sail or putting fuel into the tank. The thing isn't going to go unless you add energy to it, and you want to have the shape optimize the impartation of that energy to the fluid in a way that then requires the least amount to do what you want to do. And also, this is something that people often don't really appreciate, is that a boat actually gets some of that energy back if you do it right. When first you're pushing the water out of the way, but then behind you, the water's kind of pushing. Once the waters get past the middle and it's trying to get back together again, it's actually pushing you forward.
Especially the hollow line thing. Even this boat is very, like this bow is very hollow. Back in this section is extremely hollow in there. But there's quite a difference in how that hollow is expressed, fore and aft.
Yeah. So we use a variety of curves from straight lines to hollow curves to straight lines to full curves for different purposes in different places. And again, this is one of these things that the sooner we plug into a specific, this will become much more interesting and directed. Well, a few of you have talked about being interested in doing a rowing boat of some sort. Okay, so there were two You and you, right? So what if one of you just came out with how many people and roughly how large a rowing boat, or should it be like a crew racing boat, or should it be a boat to carry a ton of clams in, or
will it go in 6 foot seas or 6 inch seas?
Right.
Too. Think about the power. Obviously, think about the use. Think about what you're familiar with.
But just start. Yeah. A very famous boat builder, one of his who wrote a bunch of books, Pete Culler. His best bit of advice was experience starts when you begin. And this is all about trying to. We have to experience this. We can't just sort of talk about it.
And don't, if you throw an idea, we're not locking you into the idea.
No.
Just begin the thought process. Just start. Just throw something out. Like Tony says, you're talking about an 8-oared shell, or you're talking about a Whitehall style. I mean, this is essentially a rowing boat. A lot of boats, small boats, are shaped like this. Obviously it's not very fast, but it can do other stuff that an 8-oar shell can't.
Even this boat was rowed too.
By the boy.
Yeah.
The skipper didn't.
So 8-man racing shell.
Mm-hmm.
Okay.
All right. So all right. So let's just talk a little bit about what the basic parameters of that. First off.
Has everybody seen one of those?
You
MIT
know
what
yeah, because they're got them right over there. So a racing shell exists because a certain number of people with enough dough to do it find it interesting to have a sport where a team of strong people get into a boat and race over on calm water over a mile and a half course, something like that.
It's usually, or in the fall, it's like
3 miles, right. So, and then they come back to a clubhouse and they hang up the boat and they hang up the equipment and go on with their lives before 6 a.m. So as far as from a boat designer's perspective, it's really important that we not just that we don't explore the fact that there's a social component to this. I mean, this boat wouldn't exist if it wasn't important to the people who want this boat to fulfill this particular need. And we just assume that a need just is there, or that because there are 5 different niches that covers all needs. But this is a very this particular need has a long tradition, and there's been a long development to satisfy that need. So it's right now it's a kind of a boat that's been pretty well developed over the last 100 and something years, and it started out being basically it grew out of basically like a Viking ship. A lap-strake, lightweight, long, skinny, flexible hull that had 8 Vikings in it, and they'd row really fast. And but then again racing, the whole idea of racing, again it's an assumption. It isn't the only way to think about pleasure boats, but it's a basic assumption that a lot of people make right off the start, is that, well, the way to have fun with a boat is to compete with a boat. And so, of course, this is a very highly evolved version of that. So you've got teams that compete against other teams, schools, and they're often, like with MIT, there have been schools that have prided themselves on their engineering abilities, and so this has had a lot of development. So from that start, something like a Thames River barge, which was basically a water taxi in London, big, long, fairly skinny, lightweight boat with long oars, and this developed into these shells, which basically totally minimize the amount. They're displacement boats because even though they're very fast, they're quite heavy because the crews are really big and strong for the size of the actual boat. The boat, there's a lot of power, but there's still a lot of weight. So they're totally displacement hulls. But how do you get the maximum amount of displacement with the minimum amount of surface area? Well, you do that with a half a circle section, right? you know, anything where, you know, anything that deviates from an arc, a circle, is going to have more surface area for the same volume. So basically, you know, this is a big, long half of a pipe with then a pointy end at the front to break the water, and then a fairly pointy and buoyant end to you know, to hold the back up and to let the water come back together. And there's no stability to this boat, because what's the least stable shape there is? If you take a beach ball and throw it in the water, you know, it'll just tumble. It'll just keep on turning because there's nothing to keep it upright. You know, these boats are all assuming that there's a shoulder, there's a corner that's going to resist tipping. In a lot of cases, there's also ballast that resists tipping in the opposite way by, you know, as you try to bring the weight up away from its natural repose, it's, you know, it's going to fight to come back down. But in these racing shells, there's absolutely no stability from the boat, and if three of the rowers raise their left eyebrows, the thing is likely to tip over. And that's part of the sport. You know, it's part of the rigor of the sport, is that the crew has to work together in every way, including keeping the boat upright. Because if they can't even do that, they're not even going to make it to the starting line. So that means that for your particular project, if this is what you're interested in, you can either try to well, we start by looking at it in what's the current thinking about what makes the best shape for these boats, and talk a little bit about the construction, because of course the lighter this structure is, the smaller it can be, and that means there's going to be less resistance in every way, and the thing's going to be faster. But then mostly, I'm not really absolutely certain about this, but I think there are some development classes. But when two schools race, are they racing identical boats? No. You're able to, yeah, you can develop the design as well as
there are waterline requirements, aren't they?
Yeah,
that's something we should talk about too. Is what is the function of that length? I mean, this would be really basic for some of you, but you know, in a displacement hull, what is that function? Does anybody know? Yeah, a bunch of you do. I know.
You do. You just don't realize it. If you look at an oscilloscope, you know, you have a wave, right? And that wave has something to do with energy, right? And you know, whether it be a light wave or a radio wave or a water wave, you know, either the amplitude or the length of that wave, and the amount of deviation over a certain area from flat is a function of the amount of energy that's held within this wave producing system. You know, water works that way. You know, the surface of water really works that way. If you try to push something through water, that separating of the water and trying to get displace the displacement wave that happens around the boat, the shape of that wave is limited by the laws of waves that many of you are familiar with from other areas, and basically, you know, the wave for a given speed is going to have a certain wavelength, and then for a given amount of energy required to meet that speed is going to have a certain amplitude. You know, a boat that's very, very efficient for a certain speed may have a very low amplitude wave, and one that's, you know, towing a brick through water at the same speed as one of these rowing shells is going to create this horrifically high wave with a lot of turbulence. If you have a given amount of energy to power a boat, like, you know, 8 rowing, you know, pairs of shoulders and legs, then the longer you can make that boat, the faster it's going to go, because one wave is going to, you know, the length of wave that boat can create will be going at a higher speed than a shorter boat. just back up on that a little bit, that for a displacement boat to fulfill that whole function of parting the water and letting the water come back together behind it, it's limited to, at most, the fastest it can go is one wave length, right? Where there's the crest of a wave starting at the bow.
Let's look at it, in this sense. You've got that wave form. If you look at photographs, but this is the way to think about your models. Is that wave line is going to make this nice sweep.
Right.
And when
so there's a crest here, and there's a crest at the stern, or the double ender, like most of the rowing boats. Then that crest is back here. And if you try to go faster than that wavelength, then you're going to start to the equation isn't going to work out. You have to walk. The support of water is going to increase in the bow because the wave's getting higher, but the length of the wave is going to be way back here, and you're not going to get the support back here. So effectively, you go from a zero-sum energy situation to one where basically you're going uphill because the amplitude of the wave here and the length of the wave here isn't allowing you to resolve all of the forces.
And a lot of planing boats have to overcome that, and that's kind of what they do. Everybody's in a power boat that goes way up at the bow, and it's really inefficient. It's making there's a hole in the back of the boat. But then once it gets up on plane, it levels out again. There's a certain speed, but the hull is really inefficient.
Right.
But a displacement hull can be very, very efficient, and whereas in a boat shaped like this, as opposed to a 60 or 58 foot long 8-oar shell, they're about that long, aren't they?
I think they're about like 40.
I thought they were longer than that. I'm thinking of the canoes, I guess, on the Pacific Northwest or Polynesian Islands, something. Those boats are making a wave too, but it's almost invisible. It's so long and the amplitude is so low, because of that speed that length to weight ratio. With this boat is very pronounced, and you could actually tell if if you see the wave, like if this is sailing in this light air, you can see the boat. There'll be a bow wave, and then the stern wave might be here. The boat's not at hull speed. It's not at its maximum speed. But once the breeze is up and the hull gets full power, then that stern wave is back there. You can actually judge speed based on how that wave is shaped along the hull. We'll look at a lot of photographs that show that. But that's just as far as this process goes, that's just another way to think about this shape intuitively and as a dynamic.
Yeah, and see, for instance, the example of a racing shell is on one end of the extreme, where the conditions are basically always exactly the same. The power is almost exactly the same. Just on a certain day, a certain 8 athletes are going to be a tiny bit stronger than the other 8 athletes in the other boat, but that range is very narrow of the power input. It's almost as though you said, okay, I'm going to use this electric motor of 12 watts or whatever, and that's going to be the power I have, and I can raise or lower it by 1/10%, and that's how I'm going to tell who's going to win. So those boats are acting under a very, very limited set of conditions for a short period of time. They don't have to have any room for you to sleep. You can't even bring bring your lunch with them or anything.
So let's think about that. Okay, we're in the Charles, and we've got our 8-oar shell. We want to now take that boat out into the inner harbor. What changes would we want to make to that hull? How would we tweak that for that new use? We still want a fast boat. We know it's not going to be as fast as the dedicated river, flat water shells. But what about when you're out in, say, 2-3 feet of chop, dealing with wakes and currents and all the good stuff that's out there? How would you reshape that hull? I mean, what are the new requirements? Stability is a big requirement. It's got to be able to shed some water. It's got to be able to lift on the seas and throw them aside so that it can carry through. And that impacts how you row. That impacts position, the style of rowing, and it impacts the whole shape of the boat suddenly. And then, moving on from that, if you want to carry something now you're going to carry. Back in the 1850s, there were big 14-oared barges in Boston Harbor that were carrying a lot of things. They were carrying granite. They're these big. I've rowed in some of these boats. They're 38 feet long. They're 10-oared gigs, but they're open water boats with fixed seats. There's no sliding seat in the 17-foot oar. They're pretty darn seaworthy. Those boats can really go anywhere. But it doesn't look anything like a sail. You know, this boat is, I think the Bantry Bay gates are 7 feet in beam or something. They're quite wide. But still, you've got that long water line. But you have a whole other application involved.
Okay, so whoever's the most bored with the whole idea of talking about a rowing boat, what kind of boat is starting to pop up in your head? So we can bounce, have some different sides to this story.
So one thing I thought of was if we could have a boat that has maximum resistance to tipping over, it could also be designed fairly as a racing boat, but to have something that doesn't tip over and at the same time moves fast.
As a sailboat, you mean?
Yeah, something like a sailboat.
Right, right. Yeah, well, do you have roughly a sense of size or number of people or place to use it?
I'm actually quite new to this, but
no, that's fine. That's fine.
I would say 4 to 6 people.
Okay, and do you kind of use it off the coast here, or crossing the ocean, or?
Think river, perhaps.
Out in the river. For the day.
For the day.
Mm-hmm. Right, right. Well, yeah, there's even a name for that kind of boat. Call it day sailor. Okay. That's a very that's a good dozen steps removed from the rowing shell, but it's a very known type, and a very, to me, very interesting kind of boat, because it kind of boils down the other end, well, of a spectrum of ways of thinking about having fun out on the water. The other was a very regimented sport, and this is more the idea of just kind of getting out and enjoying the day on the water, and more or less being rabid or not rabid about beating your buddy who's in the next boat next to you. This particular design here, which was a lobster boat, a fishing boat from
not that one, but yeah.
Yes, well, this is the first
day sailor version.
Yeah, the day sailor version, but that grew out of a working lobster boat. This one's 20 feet, but anywhere from for 4 to 6 people, anything from let's say 18 to 30 feet could accommodate that kind of boat, and either be for the different types are there are boats for small lakes where there really never very many waves, to bigger rivers or bays where there can be fairly nasty, short, choppy waves that might be this high, and then other places where, well, there is no protected water, and if I want to go out for the afternoon, I still have to go right out up there in the nasty ocean. So this type of boat can vary from being certainly never has to be as limited in its conditions as the rowing shell, but it can be something that's evolved for a fairly limited set of conditions, or something that has to deal with anything. So it's a broad open range, and as you go along, kind of trying to hone what part of that you would like to follow, because the more specific each of you can be about what it is that you're envisioning, but step by step becoming more specific, the more you're going to learn specifically about boats and about what we're talking about as a subject matter, but also it will take you through this kind of incremental decision-making process, which is really what design is all about, and it applies to everything.
Well, yeah, the question you asked, the way you posed it was good, because you're talking first about stability. You've narrowed down, some ideas about the use, in this beginning phase, but Tony talked a little bit about the different ways of making a boat stable, and that's something you'd have to answer too. Like this boat actually originally had sort of 2 forms of stability. It has this buoyant, this section, this you know, it's fairly wide, so it's got this section here that's buoyant. So as the hull, as it presses the sail, leans the hull over, that buoyancy is resisting that shape. It also had lead cast into the keel here too, so it had both forms of stability. Some boats, you know, are very wide and shallow, and if you're in a river, that may be what you want because the river may be really shallow. Other boats may be very, very deep with a lot of lead. So the deeper they are, the bilges, this curve here, they're very slack. So there's none of that form stability. There's nothing about the shape of the boat that keeps it from going over. But that weight, as soon as you, so that's a boat that kind of has to be lean quite a bit in order for it to become stable, right? So that's something else to think about is, you know, in terms of use, if it's a shallow water environment or a deep water environment, and then all your preconceptions about how to make the hull stable. So that's a great way to think about the design right there and thinking about the model intuitively and making guesses about that.
All right, I feel like
Base sail
groundswell.
is a massive category.
Yeah,
too.
I feel like groundswell now. Now 2 or 3 people are going to raise their hand with 2 or 3 other ideas, or jumping on a bandwagon and they want to follow the same idea, but it's slightly different. So let's see, who else is ready to?
Anybody thinking about power at all? I mean, anybody think about an engine, electric, you know, gas, diesel? Anybody thinking about a planing hull? You know, real fast.
Does anybody understand what can somebody give me an example of what a planing hull, what we mean by that? Just a boat. Miami Vice powerboat, sure.
Or a windsurfer.
Okay.
Great example too. Yeah, those. And that's two very different shapes of hull.
Has anybody windsurfed?
Flat bottom. Yeah.
You windsurfed? Anybody surfed? You too? Yeah. Okay. You count as 2 for that, 2 boats. So that means you're interested in rough water and you're interested in wind and athleticism, right? So you know, a good category for you might be a high-speed racing dinghy or a sailing canoe. I don't know if you've ever heard of either of those types, but the most famous of the racing dinghies would be the Australian Ideens, they call them, you know, which have evolved now over the last 100-odd years. But they're a great example of how if you can look at designs from, you know, the 1890s that look like prehistoric versions of the boats that, you know, that you'd see in Sydney right now with carbon fiber rigs and, you know, people out on trapezes. But the thing is that they were models because at the time, you know, sailing models, you know, this big or even 6 feet long. But there was no way at that time to have materials strong enough to do such an extreme boat big enough to carry people. But they were already doing it with models. You know, the thing with what's so exciting about surfing or windsurfing or sailing, canoe or an 18 is that you're experiencing an enormous, you know, incredibly dynamic set of conditions, you know, very high energy, and that require a lot of athleticism and a lot of you know, kind of grooving on all the complexity of dynamics that's going on while you're experiencing this. You know, when if you're surfing, you know, you can't kind of like stop and think about any particular thing, but you got to keep just absorbing the whole thing all the time, right? And reacting to it. Well, that's exactly the kind of thing that design, you know, that thinking through a design is just like surfing that way, and that, you know, you can't get bogged down in any particular idea, but you've got to allow yourself to gain experience just absorbing a wide range of dynamic parameters so that then you can actually ride this wave to some conclusion. But anyway, so there's all sorts of interesting things that we can go from there.
And this, another interesting thing about that kind of boat is that your ballast, the system you use to hold the boat up is suddenly is you, right? So instead of the weight being concentrated in the middle of the boat and immovable, suddenly the weight is way out here, right? Your weight on the side of the hull that is going to keep it upright. So that's something else to think about as you're thinking about design. Is that's another dynamic element.
Yeah, see, in the racing shell, it's kind of like a tightrope walker with a great big bar. You know, you've got the oars, and the fact that you've got people who are very sensitive to their balance and their equilibrium are all trying to kind of balance in the middle of this very tiddly thing. And that's one kind of experience of human stability. You know, gaining stability for the vessel just by the crew doing a job. But in a windsurfer or a sailing canoe or a sailing canoe is basically a little skinny boat, not much different from a smaller rowing shell, you know, with a hemispherical bottom to it, or you know, basically starting with a hemisphere and then tapering to a planing surface, but you know, this wide, and then a sliding bar or a trapeze that lets you be out, you know, 6 to 8 feet away from the center of the boat to hold it upright. And then when you tack, when you change directions, you've got to get from that one side over to the other fast enough and smoothly enough to keep the thing upright.
And it doesn't have a pontoon?
No, it doesn't have anything.
No,
it's just you know, this dynamic human stability. And in an 18, you've got 3 people on trapezes. Everybody that's on board is in a trapeze, and they've all got to get around to the other side somehow and hook and unhook or whatever, swing around to keep this thing upright.
Yeah, in sailing canoes, the stability is different when you're moving. That's one of the real challenges. I've done a lot of sailing canoes, the old 19th century. That was yachting, you know, for poor people around 1890. And I've worked on a bunch of those boats. But when you tack, when you come about onto another heading and sail, those boats really stall. They almost get so they're standing still. And if you fill the sails too quickly and you react too fast with your weight, it will just lie over on you. So you have to, the pressure in the sails varies with your speed. So you're constantly sheeting in and making, so that's another part of the dynamic nature of those boats. Yeah. This is another thing about rowing too to consider, is that there's a weight side to side, but in rowing you've got masses of weight sliding fore and aft, right? And so that's something the rowers, I know, work on that quite a bit, trying to be very smooth in that transition, right. You know, throwing your weight. But the hull has to resist that sudden massive weight moving forward and then sliding back without pitching, without inducing drag or influencing that wave in a negative way too.
Yeah, see, again, a really exciting thing about thinking about the dynamics of a boat is that the water will resist, but ultimately never just block any force that you put into it. You know, if you're building a building or a skyscraper or putting up a tent or whatever, you basically can count on the ground being more or less resistant, and that you can pretty much you've got a fair amount of leeway as to whether or not you put a lot of the weight of a structure over on the one side, and you have another part over here that doesn't have much weight over it. As long as the thing isn't overbalanced, it's going to stand. Whereas with with a boat interacting with water, the water is just always working to transmit that force, resolve that force somehow, and it has to do it all between the water and the boat. And so if pitching forces or heeling forces, which are tippiness or speed forces and interaction with waves, all of those things have to be resolved between the boat and the fluid. And there's no external foundation that you can rely on to hold the thing upright. Okay, so now we've got 3 of the basic types of boats covered. We've got a very narrowly defined human-powered racing boat. We've got a pretty broadly defined pleasure sailboat, and then we've got a very dynamic sail-powered but human balanced dinghy or sailing canoe. Is anyone not interested in any of those types, but more interested in something else?
What about like a motorboat or something having the power from the back for like 3 to 5 people or something like that? And how does the shape
Yeah,
Because
well,
it does plane.
First
or
off,
something.
what's it going to be used for?
Just for like a day or out on a lake or something like that.
Just to tool around?
Yeah, I guess, or even actually an ocean one would be interesting, like how
Okay.
that.
But, okay, so let's just narrow down a little bit more, because, you know, boats are expensive, they're a lot of trouble, and they're a lot of trouble to deal with, to deal with. So if they don't actually, if you haven't thought through what you need it for well enough to be able to express it to whoever's designing it, in this case it's the same person since you're designing it, then the chances of you being disappointed with it later are going to be very high, because it's like, oh, I never really thought through this assumption, and I really didn't mean that I wanted to be, pounding through, on my way out to the Bahamas for the weekend, listening to the Miami Vice theme song, when I really meant to be puttering an electric boat on a lake in Maine. So if you can narrow it down.
What about like kind of like an intercoastal kind of boat, like maybe that would go behind? I mean, not to get those huge waves,
Well,
but something you could also
there's
use
an
on a
intercoastal
lake.
waterway that goes all the way from here, basically, all the way. You can go all the way to Texas, where you barely ever have to go outside, and mostly there's either canals or bays or rivers that you take, and that's people they'll do a kind of a round trip where they'll come wherever you start. Let's say start in Boston, you go down, take the intercoastal all the way down through Florida, and cut across and go along the Gulf Coast, and then go up the Mississippi River, and then take canals and things and get themselves to the Great Lakes, and then you do the Great Lakes, come out the St. Lawrence River, and then come down there. A few open parts, but mainly you can do that. You can do that whole big trip. Spend a summer or whatever. What would be an ideal boat for that? For instance, does that sound like that might be your project?
Something like that.
Okay, well, see how much easier this is getting? So.
Yeah.
Yeah.
This is a question. What about materials?
Oh, yeah. Well,
like
materials.
between like the
Yeah.
lightness of like fiberglass to maybe the extreme of concrete, for example.
Sure. Yeah.
Say like just basic operation just on Charles River for a couple miles. Like, how are the differences of materials going to affect, like, say, constructions or?
Right. Well, yeah, it's a big question, and once you start getting to the point where we just got with what's your name now? Allison. With when we just got with Allison's project, one of the next few steps would be to start thinking about material with the your name? Dwight? Yeah. With Dwight's boat, we're pretty much already set with the material. It's probably going to be carbon fiber hull that's cured in an autoclave, and because again, this thing has to. Like, another thing about those forces, the pitching forces of the crew rowing back and forth. It's not just the forces on the water, but the forces on the structure. This little skin, for you architecture people, you've got this tiny little beam, lengthwise, and you're putting all of these torsional stresses on it all the time. And if this thing starts to buckle or to waggle, it's going to destroy the flow. Because obviously, if flow is going to be quicker if it's nice and smooth than if it's all of a sudden it's being pushed and pushed. Yeah. So there, we're already pretty much certain that that's the material we would use for his boat. For your name again? Sebastian's boat. We'd probably want to go with either carbon fiber hull, but that might end up being more expensive than we'd want to go. So that might end up being a foam core fiberglass hull, or if it was if he really wanted to either do it himself or have it be a kind of a development boat that wouldn't require as much capitalization to go from one stage to the next. It might be one of the modern composite wood hull forms, and no one's said that they wanted to make the stone barges like Reuben was suggesting, but for the Normandy invasion, World War II, they made concrete barges that then they used to carry stuff over to the beaches, and then sunk them there on the beach, and then turned into the, you know, they call them the mulberry docks that they then tried to use as a harbor, you know, on this open beach. So
you're aware that architecture has a competition right now? Did you
no.
know that?
One of the things,
Yeah.
architecture has a competition right now where the idea is that something has to float and presumably move down the Charles River. So I don't know whether that's why.
Well, I'm not in a competition, but I'm just curious.
Sure,
that,
sure.
I mean,
But out of concrete?
concrete.
It has to be
as a material,
concrete.
yeah.
I mean, I can't remember the exact. I was part of the original committee,
Yeah.
but the idea being that it has to be concrete and it has to. It doesn't have to be on top of the water.
Sure. Yeah.
It can
Yeah.
be under the water.
Yeah, yeah.
But it has to be able to. Some part of it has to be able to be inhabited.
Yeah. Well, you know, part of that whole the wow factor of that question goes back to the, you know, that kind of the question used to stump little kids. It's like, what's heavier, a pound of feathers or a pound of lead? I mean, it doesn't really matter whether boat's made out of concrete or made out of feathers. It's still going to float if it's big enough to display, or you know, if it's has enough buoyancy to displace its own weight. And so there's nothing particularly amazing about a boat being made out of cement or steel or lead even. I guess it's kind of amazing. But or you know, like the Mythbusters a while back, they tried making an airplane model out of cement. That kind of didn't work because they didn't understand aerodynamics at all. But it would be possible too. You could make an airplane out of cement if you wanted to. But also it's scary because it means that the 70s never do die, do they? And I mean the 1970s, not the. There was a big fad in the 1970s of people saying, well, we can make our own big cruising sailboat and sail around the world out of cement,
The stone boat.
without having to learn how to build a boat because it's easy to make these things out of cement. You know, basically it was a big wire mesh. You spent a lot of time creating a wire mesh, you know, and then a few terrifying hours pouring cement into it, and then a decade or more watching this thing deteriorate while you figured out that you couldn't, since you didn't know enough woodworking or metalworking or whatever to complete the boat, you never got any further than that. And then, you know, a lot of these things, of course, cement to be light and strong has to be really well engineered, and it's not the kind of well, I can pour a patio so I can build a cement boat. You know, it's a very tricky medium to work with. With a lot of drawbacks.
And ferrous wire in saltwater environments.
Right.
Not very good.
Right. It has a lot of drawbacks with very few. All of the kind of obvious, what you might think of as obvious selling points for it are really, none of them are true.
Yes, yeah. In terms of construction too, I mean, the capitalization is a big thing, and that's just another element to this method in terms of capitalization. Is that this method? One of the reasons why this half-hull carving method, for people for whom it works, is still viable is that it doesn't cost anything. You don't have to buy a computer, you don't have to buy a CNC milling machine, any of that stuff. You can design and loft the boat, for a couple $100 in materials, and that's one thing that reason why it still works. And also, wooden boat building, if you're building one boat, still a pretty good way to go, because it's the tooling time and setup time is nothing like a fiberglass boat. And the fiberglass boats are getting cheaper to tool all the time, but it's still right up there. You still need a big room. You need a 5-axis milling machine to carve that foam block and all that stuff. So that's another element of this method, is to have in the back of your mind.
Yeah, for instance, now with the projects that we've got lined up, you're gonna have to help me with the names for another couple.
Oh, I'm
Dwight's boat
got like 4 out of
is going to be a very highly engineered structure. It's going to be built in basically kind of a laboratory, I'm sorry, you're
Aftab.
Aftab.
Yeah.
Yes. Aftab's boat could be built by Reuben in his shop, or it could be built in a laboratory, or anywhere in between. And Allison's boat could be built in Reuben's shop, or at some it doesn't have to be too esoteric in how it's built.
My shop is 28 degrees right now.
Yeah. And
That's why I love
Sebastian's
coming here in
boat could be built in his garage, or it could be built in a lab, you know, anywhere within that range. And mercifully, none of them are going to be built out of concrete.
As far as like adding, so like, if you had like a motorboat and a sail, like how does that affect? If you had bolts,
Have both, yeah, sure.
How does that, I guess, affect the dynamics of the boat?
Yeah, well, yeah, we kind of short-circuited your whole analysis here. I feel like the amazing president, you know. It's like, all right, I'll tell your future. Yeah, you know, your boat, it could either, you know, be a, I mean, there are different themes that you could bring to this. You could say, well, I want to be able to watch my soap operas every day, and have chilled, you know, drinks in a microwave, and make sure that, you know, my frozen pizzas are going to be well taken care of, and have this thing basically be like a floating Winnebago that then you take down an ocean highway instead of on the highway. Or on the other hand, you might say, well, you know, I'd love to see all of this area and with as low impact as possible.